Unit 7, Lesson 4, Proving the Area of a Disk. The purpose of this lesson is for students to use inscribed and circumscribed polygons for a circle, otherwise known as a disk, of a radius r and circumference c to show that the area of a circle is 1/2 the circumference times r, or as it is usually written, pi r square. For this opening exercise, the following image is of a regular hexagon inscribed in circle C with radius r. So you've seen a hexagon before. In fact, you've even constructed it in the beginning of the school year. We're asked to find the area of triangle ABC in terms of S and H. And as you can see, we have 6 equilateral triangles here. S represents the base of one of the triangles, H represents the height, and the R represents the radius. And of course, these are all equilateral triangles, so S, H, and R represent the values for all 6. So we're going to find the area of triangle ABC in terms of S and H. So we know that the area of a triangle is equal to S times H divided in half. So now we need to use our answer from part A to find the area of the inscribed hexagon. So we know that there's 6 equilateral triangles, so 6 times SH divided in half is equal to 3 times SH. The perimeter of the hexagon, this is the sum of all the sides, and we know all the sides are S, and they're equal sides. So to represent the sum is going to be 6S. Here's example 1. To approximate the area of a circle, we can use polygons inscribed in the circle. Looking at the pictures below, answer the following questions. So notice that we have a square inscribed in a circle for the first diagram, and for the second diagram, we have an octagon inscribed in a circle. So for part A, would using the area of a polygon circumscribed about a circle be an upper or lower approximation of the area of the circle? So since the area of the polygon circumscribed, okay, so that's more of a picture about a circle. So here's your circle, and if you had a polygon, for instance, a quadrilateral, circumscribed about it, would be an upper approximation of the area of the circle, because the polygon is bigger than the circle, so we're thinking in terms of area outside of the circle. Part B, of the polygons pictured, which would be a more accurate representation of the area of the circle? So the area with the octagon has more sides. And a definition in math is that as the number of sides increases, then it covers more area, thus representing the area of the disk better. So it has a closer or better approximation. So how can we get an even more accurate approximation? All we have to do is increase the number of sides of the polygon. That's, of course, inscribed. Example 2. So to approximate the area of a disk, we can use circumscribed outer polygons, looking at the pictures below. So we're going to answer the following questions. Would using the area of a polygon circumscribed with a circle be an upper or lower approximation of the area of the circle? So as you can see, it's definitely an upper approximation. Because the figure that's circumscribed about the circle is bigger than the circle itself. So we've gone beyond the boundaries of the circle. Of the polygons pictured, which would be a more accurate representation of the area of the circle. Of course, it's the one with less area difference here. So that would be picture number 2 with the octagon. There's a smaller amount of exterior space. And how could we get an even more accurate approximation? All you have to do is increase the number of sides. So if we were to draw the segments that join each new vertex in between a pair of existing vertices, the resulting 2n polygon has a greater area than that of the n polygon. So there is an inequality that is displayed. It is the area of a polygon is going to be less than the area of a circle, which is less than the area of an increased amount of sides polygon. So we're going to represent that as 2n. What if we sandwich the circle between the inscribed polygon and the circumscribed polygon? As you can see, there's less area. So the two figures sandwich the circle between them. See the red line? Which leads us to believe that as the number of sides of the polygon gets larger and larger, or as it grows to infinity, and as you can see, this is how you write it, the number of sides grows to infinity, and typically read as n approaches infinity, the difference between the area of the outer polygon and the inner polygon approaches 0. When approaching a number, this is called the limit. And this, my friends, is what you see, or what you talk about, or what you examine, what you study in calculus. Areas under the curve, or rates of change. So the area of the circle is the limit of the areas of the inscribed regular polygons as the number of sides of the polygons approaches infinity. So in example 3, we're using the opening exercise and derive the formula for the area of the circle. So as you can read, the area is equal to 1/2 base times height, and that refers to the area of a triangle, which we already know. In terms of this hexagon, we've translated it to the area is equal to 1/2 s times h. And using your answer from part A, find the area of the inscribed hexagon. Okay, so we know that a hexagon has 6 sides. We're going to multiply that to the area formula of the triangle, in which case we get, or we did get 3sh. So they kept it as 6 times 1/2 sh, and then they regrouped it as this formula right here. So what does 6x represent? We know it represents the perimeter. The perimeter of the hexagon, sum of all sides. We're going to rewrite the area of a hexagon formula using our answer from part C. So we know that area is equal to perimeter, 6s, times 1/2 h, and that is a derivation. How would this look with a square inscribed in a circle? So we know area is equal to 6s for a hexagon. So for a square, it would be 4s. So the perimeter of the square is 4s times the height divided in half. And if we simplify, we get 2sh. Do you think this will work with all polygons inscribed in a circle? For sure. So now using the same concept, we can derive the formula for the area of the circle. I know you don't see it at this time, but we don't have time to get into the derivation of the area formula for a circle, so we're just going to leave it at this. We know what the area formula for the circle is, so we're going to leave it as such.